Last summer, I was on the West Coast with my dad and my brother, and we were visiting some schools like Caltech and Stanford and Berkeley. And at the Berkeley, I was looking at the Berkeley labs, and I was kind of curious on what they did. So I asked my dad, and we saw this experiment on Brownian motion that the physics majors did, and like we thought it was kind of interesting, and we thought we could do it at home and like kind of related like the microscopic worlds to like the kind of the real, well, not the real, but like the visible world. So then we thought we could do that at home. So first we had to set up the system to get the data. So then we got this inexpensive microscope that could zoom up to 2,000 times with a camera on it. And then we got some 100 nanometer and 500 nanometer particles. And originally the microscope came with this, but because these particles are so small, they're either at or below the limit at which this microscope can image, which is why we got a UV light, which, because these have europium in them, they would fluoresce red, so letting us actually image it. And then we got this battery right here, so when you turn it on, you might be able to see some of the particles. I'm not sure, they're quite small. And we got this cooling system right here to keep everything cool, because as everything heated up, it would change the viscosity, which would invalidate the data. And we also tried to experiment with some other setups, like this one right here, that shined the UV light from the above, but if you like put the slide on like this, but we found that a lot of the light would reflect back into the camera and just kind of make everything purple, so it wouldn't really work that well. So we found this was the best. So if you think about the equation for a little bit, it's going to be the diffusion is going to be proportional to the temperature and inversely proportional to the radius and the viscosity. So then we thought we couldn't really change the temperature very well, and in like a controlled way, and the radius we can only change by a factor of 5. So then we decided we were just gonna change the viscosity by a factor of like 1,000. So first we tried to use this polyacrylic acid, and as you can see, it didn't really work very well, because this one is twice as dilute as this one, but as you can obviously see, they're definitely not twice as, this one's definitely not like half as viscous as this one. So because it's a non-Newtonian liquid, this change in viscosity varies a lot, like it has a very exponential curve, so it didn't really work very well. And also on the test we tried to do a drop test, and this tube is filled with this solution right here. This BB has been dropping for about a month and it hasn't really moved, so we couldn't really test it very well either. So then we switched to a Newtonian liquid like sugar, and we found this paper from 1958, and it was this chart on like how viscous, can you see that? How viscous like thing will be, like water will be when mixed with sugar, when it's like up to 75% sugar, and it goes all the way up to about 4,000. So then we decided we were just gonna add as much sugar as possible to water, but it turned out it didn't really stay in like a solution very well, and it just crystallized, so we can't really do that. And even in ones that are like kind of viscous but didn't like crystallize immediately, they weren't able to be vortexed by this vortexer, so we couldn't really like distribute all the particles through it very easily. As you can see, it doesn't mix at all really. And when you heat it up to decrease the viscosity and try to add them, the europium degrades in heat very easily, so then we can't really do that either. So then we just settled on using some less viscous sugar solutions like this one and this one right here to measure it. And we decided to use these because these can like vortex very easily, as you can see, and we can mix the particles through them very easily. And they didn't quench the fluorescence a lot, because sucrose at high concentrations can quench the fluorescence, so you can't really see it as easily. So to measure the viscosity, instead of using this drop test here, we used this right here, which is a 3 milliliter syringe and it's filled with solution. It's just water right here. So you take the top off and you unscrew the cap and then you just let it drop. So then we would record that and see how much time it takes to drop from 3 to 1. So then we had to set up all the image processing. So then for each frame we split it into a red, green, and blue layer, and then for each layer we applied a Gaussian filter of 2 pixels to get rid of all the staticky noise that the camera produced, and then we did another layer that did a filter of 100 pixels to get rid of all the background noise, and then we subtracted the first layer from the second layer to get rid of all the background and just illuminate the signal, and then we filtered that frame a few times with a repeating 2 pixel filter and 10 pixel filter, which really just sharpened like all the real signals. And then we made a cutoff and we took the top 99th percentile of brightest pixels on the image, and we did that for all the red, green, and blue layers, which gave us 3 binary black and white images for each picture. And it would only, so then we layered each one on top of each other, and for it to count as a real pixel and go into the final image, it had to be white for every single layer. So if it was white for red, white for green, but black for blue, then it wouldn't count it. But if it was white for all 3, then it would count it. And so then that produced the final frame that would go into tracking. So then we had to do the image tracking. So then we ran a function that gave us the XY coordinates of the center of each particle and the area of that particle in pixels. And starting from the first image, we created one track for each of those particles. And then from frame to frame, we assumed that the nearest particle of the similar size was the location of that particle in the next frame. And we repeated that 1,800 times because the camera took 30 frames per second, and we ran it for 1 minute. And this gave us the XY coordinates and areas for all the particles for the entire minute. So then for each particle, there's around about 1,800 steps. So then from frame to frame, we took the change in Y and the change in X, and then we found the difference from each step for both the X and Y, and then we found we squared that difference, and we found the mean of it for both X and Y, and that's the mean square difference that is used in the Brownian equation. So then to calculate Avogadro's number, there were 2 kind of most challenging parts, which were calibrating the length scales from pixels to real measurements, and then also doing the dimensional analysis. So then to calibrate the length scales, we used a calibration slide and mapped the number of pixels per micrometer. And what was interesting was that we found that the field of our camera was around about 1 millimeter by 0.5 millimeter, which is pretty small. And the second thing for doing the dimensional analysis right is picking the right units for the ideal gas constant, viscosity, and the temperature in Kelvin, so everything canceled out. To summarize, we originally set out to see if we could find correlations between temperature, radius, and viscosity in the Brownian motion diffusion equation. And then we realized that we couldn't really change the temperature that much as it's in Kelvin, and for the radius we couldn't really image these 100 nanometer particles in sugar because it would just quench the fluorescence too much. But then we realized that the Boltzmann constant used in the equation is equal to the ideal gas constant over Avogadro's number. And after doing some research, I kind of realized like how kind of interesting Avogadro's number is and how widespread it's used in chemistry. So then we changed my mission to try to calculate that. So at the end of Einstein's 1905 publication on Brownian motion, he invited, quote, an inquirer to use his equation to try to determine Avogadro's number. So after doing some research, a physicist in 1908 named Perrin did this experiment using gamboge, which is a paint that can produce like very fine and spherical nanoparticles, which took him like several months to produce. And he ended up calculating Avogadro's number to be 6.02 times 10 to the 23rd. And in 1926, won the Nobel Prize in Physics for calculating Avogadro's number. And after doing all these experiments and calculations, we ended up getting our answer to be, for Avogadro's number to be about half that. So it was about 3 times 10 to the 23rd. So I'm assuming at this point that errors are coming from optical errors in either the microscope or computation, and just because our equipment just isn't that advanced. So then after doing all this and calculating Avogadro's number, there was asked myself a few interesting questions. So, for example, I was kind of curious to see what would happen if we had a wider range of nanoparticle sizes. So then we did an experiment using some polystyrene nanoparticles we made by dissolving styrofoam in acetone, and kind of seeing how the size kind of varied and kind of changed. The diffusion rate was pretty interesting. So in conclusion, the whole experience of this was kind of really eye-opening to see how a fully fledged complex experiment is conducted, and it's a lot more challenging and involved than I originally thought, and kind of seeing the combination of experimentalization and theorization to get a natural constant of nature that's really commonly used in science was really cool to get. And kind of seeing the trial and error of building an experiment from scratch, and also the computation was it was tedious, but it was also rewarding in the end. And the day-to-day grind of just keep on getting at it, and finally achieving that goal was really rewarding as well. And I'm hoping I'll be able to do all this with a bunch of other motivated people, and just kind of do it with all the proper equipment so I can fully do this to my ability, and just try to be my best kind of self.